Hello everyone. I'm Nahid Anwar. Today I'm going to talk about the length extension attack. So before I start talking about the length extension attack, let's first talk about Markel-Damgard construction. We know that in the Markel-Damgard construction, a message is divided into some blocks. An initial vector IB with the first message block will be put together as inputs into a compression function. The output will be a hash value with the next message block they will put into the next compression function, and so on. Finally, this construction will produce a hash value which we call H of the K concatenation with the message M, where K is the symmetric encryption key. So what is the problem with the Markel-Damgard construction? The problem with this architecture is that an attacker can use the final hash value, which is the hash of K concatenation of M. Using another message, let's say M prime, the attacker can calculate the new hash value, which is H of K concatenation with the original message with the concatenation of the new message, without knowing the original message itself or even not knowing the encryption key. This is known as the length extension attack. So here I have shown how this will work. Now let's talk about the MAC. MAC stands for Message Authentication Code, which is used for authentication when messages are sent from one person to another using symmetric key encryption. Senders use encryption key K and the message M and put them into the MAC algorithm to produce the message authentication code. Together with the message, the sender sends the message to the receiver. The receiver, on the other hand, will produce MAC using encryption key K using the MAC algorithm and will try to check whether these values are the same or not for ensuring the authenticity of the sender. So what is the problem with this MAC? So there are two ways for generating MAC. One is the H of M concatenation K, and the other one is the H of K concatenation with M. The second way is vulnerable to the length extension attack because this hash function is based on the Markel-Damgard construction. Therefore, length extension construction is basically concerned about be able to take the second form of this MAC, which is H of K concatenation M, and producing the new hash, which is H of K concatenation of M concatenation of M prime, assuming that M prime is known previously. M prime is known regardless of the padding of the original message. For the attacker, he has to know the length of the message as well as the hash value of the final message of the original message. So when Bob or the intended recipients receive the H of K concatenation M with the concatenation of new message, the new message M concatenation M prime from the Oscar, the bad guy, he thinks that it is coming from Alice, the legitimate user, but he finds out that the signature or the MAC or the hash value he got each matches with the received new message, because and more interestingly, the key can be used only once by the Alice and the Bob, since except two of them no one knows the key K. This way length extension attack works. So this is an example of length extension attack I'm going to demonstrate. So let's say a server for delivering waffle of a specified type of specific user at a location that could be implemented to handle requests of the given format. So this is the original data or the message that will be sent, and this is the signature that is generated. This is the hash value or the signature that is generated using this original data. So the idea is the server will perform the request if and only if the signature is valid, definitely for the user. The signature used here is basically, as I already mentioned, signed with a key. Definitely it is only known to the sender and the server, but not to the attacker. It is possible that for an attacker to modify this request, in this example, by switching the request from request waffle from ego to liage. This can be done by taking advantage of the message format. So it is now the desired data is something like this, where the message has been changed at the last, which is OFL equal to liage. To sign this new message, typically the attacker would need to know the key of the message by which it was signed earlier, and generate a new signature so that he could generate a new MAC. However, with the length extension attack, it is possible to feed the hash value into the same state of the hashing function and continue where the original request had left off, considering the condition that the length of the original message is known, as we already mentioned. In this request, therefore, the original key's length is 14 bytes, which could be determined by trying forced request with various assumed lengths and checking with the length result in a request that the server accepts as valid. So the padding is needed for the message that will be fed into the hashing function, as many algorithms can only work on input messages whose lengths are multiple of some given size. The content of this padding is always specified by the hash function that is used in the architecture. For example, the block size of SHA-256 is 64 bytes. So a message will be padded to the multiple of 64 bytes during the hash calculation. According to the RFC 6234 standard, padding for SHA-256 consists of 1 byte of x80. You can see this is the original message, then 1 byte of x80, followed by as many zeros, followed by the 64-bit 8 bytes length field at the last of the message, which is you can see this 1, 2, 3, 4, 5, 6, 7, 8. These 8 bytes are the length of the message, original message, and between these are the zeros to make the padding successful. Finally, the new signature will be generated, which will be look like this. This is the new signature. So after sending this new message, which is this one, the new data here, with the new signature, this is the new signature. The receiver will verify this information as legit, although it's coming from the bad guy Oscar. The most interesting thing that the Oscar does not have any idea about the message M and the K itself. This way, length extension works. Thank you.